we are trying to understand whatever in our theory class we have explained regarding stability of airplane, that is static stability in particular, and more specifically stick fixed static stability. And what was the problem? We solved a problem where we said there is a configuration, wing and fuselage, whose Cm versus alpha graph, alpha plot was based on this linear equation, and you know that this is nothing but Cm naught. We realize this value is Cm alpha, so it is basically Cm wing fuselage is represented in this fashion. And when we check this number, we found that Cm alpha is negative, so it is statically stable configuration. However, we found Cm naught is also negative, so it is not possible to trim it at a positive angle of attack, right? Barring that simple understanding, we always remember that for a cambered aerofoil, there could be a negative angle at which you can trim. However, in general, we try to trim an airplane at positive angle of attack, and if Cm naught is negative, we know that it is not possible to trim. This is Cm, and this is, let's say, alpha or Cl. So if Cm naught is negative, this is Cm naught, then the trim is at negative angle of attack, which we do not want. We want something like this. It should be trimmed at positive angle of attack. This is what we are looking for. So this, we understood that this cannot be trimmed at positive angle of attack with this sort of a number. So the problem was given, why don't you change this whole Cm wing fuselage, and now you have to put a tail, and so that it is represented by this expression 2.5 alpha, where you could see that first we are not talking about tail. That means we have to add a tail. The tail will do two things. One is it is now making Cm alpha more negative from minus 0.0035 per degree to minus 0.025 degree per degree. So it is becoming more statically stable, and also now the tail should be such that Cm naught also becomes greater than 0, so I can trim it at positive angle of attack, right? And we solved this problem, and we found that what is the tail volume ratio required or tail area required, we found out, and also we found out what is the tail setting angle. So these things were done. This is one of typical real life design problem. Generally, you design a wing thinking in terms of how much lift it should be able to generate, because the area of the wing is very important, as the lift is the primary component which produces lift to balance weight or to produce enough lift more than weight whenever maneuver is required. So we are now very clear that wing is primarily to generate lift and tail for stability. Stability plus trim. This is the primary role of a tail. Okay. It doesn't mean in longitudinal case you will see that wing also contributes to trim, provided you very smartly you locate aerodynamic center and the CG of the whole airplane in a particular fashion. However, that is not the primary aim of the wing. Okay? So that part of the problem was more focused towards stability and trim. When I say stability means I said static stability. Okay? Now the second problem we'll be doing, which is more a general case. This problem will help you to understand, to refine your understanding in terms of, number one, CL alpha 3D from CL alpha 2D of an aerofoil. Number 2, it will also contribution of wing and tail towards Cm naught, towards Cm alpha, and third, stick fixed neutral point. Remember, I have been constantly telling you I'll be solving some practical problems so that you don't get lost into all those expressions. At once the expressions, you know, for the first time, you know how it is to be derived, then more important it is how do I use it. But finally, I am going to design an aircraft. Okay? So with this in mind, now I'll be solving a problem, and let me define the problem. Let us concentrate on the problem. See, I have given some number for a general aviation aircraft. Typically, these aircrafts are below 1500 kg class. It could be Cessna 182, it could be Piper Saratoga, around that family of aircraft. What is the information we have? Let us first understand this information. About wing, what is said? CMAC wing is minus 0.1116. What is the meaning of that? What inference we get about from this information is that it is a cambered aerofoil. Okay? Correct? Because there is a CMAC wing present. Had it been a symmetric aerofoil, CMAC wing would have been 0. So one thing we understood is a cambered aerofoil. For a lift coefficient, this is 2D value, right? Which is 0.097 per degree. Be very careful. Generally, you operate in terms of per radian, right? So many books also will be using both per degree and per radian at their convenience. But we should be very clear that this is per degree. So if I want to convert it into per radian, so I have to just multiply it by 57.3. Okay, that is 180 by pi. Then again, alpha 0 means alpha at lift equal to 0 or CL equal to 0. Since it is a cambered aerofoil, from here we have inferred, so this is minus 5 degree. That is, if I try to draw it, CL versus alpha, this is CL, this is alpha, this is that minus 5 degree. Okay, this is typically of cambered aerofoil. IW is the wing setting angle. What is this wing setting angle? If you again recall one of my lectures, I have explained this. If this is the fuselage reference line, the wing is set at some angle with fuselage reference line. This is called IW, or wing setting angle. Okay, and that wing setting angle is 1 degree. Clear? Now come back to the tail. This is the tail portion. Let me write tail here. CL alpha, now you see it's a capital L alpha of tail. That means it is 3D value. Already 2D effect has been, 2D aerofoil value has been converted into 3D value. So this is directly given 3.91. Now it is given in per radian. Okay? So CMAC tail is given as 0. That means the tail aerofoil is symmetric aerofoil. Then IT is minus 1 degree. And what is IT? You can check my lecture. If this is the tail, I will be putting the tail like this. And this is IT equal to minus 1.0 degree. So the tail is not like this, tail is set with a minus setting. Why this tail is put as a minus? You know by now that at alpha equal to 0, suppose this is not here, suppose this is wing is like this, then at alpha equal to 0, tail will experience a force in this direction, and about CG, it will give a value positive Cm. So we say we'll get some amount of Cm naught positive by giving a tail setting angle negative. Correct? Why this Cm naught positive I am talking here now? Because we know that if I want to trim an aircraft, at a positive angle of attack, I have to ensure that Cm naught is greater than 0. Okay. So this is the description of the airplane. What is the task? Task is to calculate contribution of wing and tail for Cm alpha or dCm by dCl, whatever you want to compute, and second for Cm naught. Third, we need to find neutral point. Neutral point, stick fixed. We are talking about stick fixed. The question is clear? With this configuration of an airplane, we want to calculate the contribution of wing and tail. We are not including fuselage. We will have one session on fuselage. So we are now focusing on contribution of wing and tail towards Cm alpha or towards static stability, or Cm naught towards stream, and find any neutral point for stick fixed case. Okay. So let us solve this problem. Let us again come back to this configuration. One of my advice to all of you would be, just don't start solving a problem seeing some numbers using some equation. Try to look through those numbers and visualize an aircraft. Okay, that will tell you many more things than what I am being telling you or what the numbers will tell. If this is the wing, tail is somewhere here. Tail is symmetric, but tail is not only symmetric, tail is set at -1 degree. So we should correctly draw it like this. This is -1 degree, and this wing is cambered. So I should at least pictorially draw it's a cambered aerofoil. Okay. We are neglecting fuselage. What is more information we have? We have, let's say this is the fuselage. I'm just drawing dotted line. We have location of CG somewhere here, which is 0.295 C bar, and AC at 0.25 C bar. Okay? This is clear? And further, you could see LT is given here. LT is what? LT is the distance between CG of the airplane, this is CG of the airplane, and the AC of the horizontal tail. So this is LT, and this is given as 16.0. Clear? So now you have got a picture. What information you get from here? From this drawing, we understand that wing is a cambered wing, tail has a setting angle. What more? Very important thing is here, since we want to calculate Cm alpha of the whole aircraft as equivalent to Cm alpha because of wing plus Cm alpha because of tail, of course Cm alpha because of fuselage, we are putting it to 0 and neglecting it. So as far as Cm alpha of the wing, one thing you should immediately get, and it should be very, very clear, and that will show how much you are understanding it. If this is the CG and this is the AC of the wing, one thing I know, the AC of the wing is ahead of CG of the wing. AC of the wing is ahead of CG of the wing. So the contribution of wing towards stability or to Cm alpha will be stabilizing or destabilizing. We know that for it to give a stabilizing effect, the AC should be behind CG, right? If I again try to help you think, remember if AC is behind CG, so if there is a disturbance, then force will come here, which will give a nose down moment. So for a positive alpha, there will be a negative pitching moment, so Cm alpha will be negative, so that leads to static stability. Or in other term, I say, because AC is behind CG, so the moment there is a disturbance, it will generate this force CL, which will give a pitch down moment, or it has an initial tendency to come back to equilibrium again. That is, so alpha equal to 0 or alpha equal to any alpha desired or alpha star. Cm alpha sign for wing, you will find it should come positive, because this is destabilizing. Second thing what you understand, for tail, you could see AC of the wing is behind CG, so it will have stabilizing component. So Cm alpha will be negative. You could see from here also, if there is an alpha, there will be force upward, which will give nose down moment about CG. So this aft tail, which we are talking about now, and I'll be addressing it as tail, is always stabilizing. The moment you put a canard or something here, which is called forward tail, then it becomes destabilizing, because the AC is now again ahead of CG. Okay. We are now do a calculation how CL alpha 2D can be converted to 3D. Right? The formula which you already know, CL alpha 3D is equal to CL alpha 2D by 1 plus CL alpha 2D by pi aspect ratio. I am taking E as 1. Right? Now let us do it. What is the aspect ratio for the wing? We have to calculate aspect ratio for the wing, and we know aspect ratio is B square by S. What is B for the wing? Somewhere it is 33.4 feet. 33.4 square by S is also given 184. So you will get a value which is equal to roughly 6.06. Right? So this is aspect ratio of the wing. Now it's very straightforward. CL alpha wing 3D will be, what about CL alpha 2D value? Let me put that 0.097. This is per degree. So I will multiply it by 57.3 to make it per radian. 1 plus again 0.097 into 57.3 divided by pi into aspect ratio, which is 6.06. And if we do the calculation, if I am not wrong, this is 4.3 per radian. This problem is also from Nelson, which I showed you yesterday. So those who are interested, they can see this problem there. But let us understand. This problem I am using to synergize whatever I have talked about stability. Similarly, you see for control as well. Okay, this is fine. Now, what is our aim? We know Cm equal to Cm naught, Cm CG of the aircraft, Cm naught of the aircraft plus Cm alpha of the aircraft into alpha, right? We are not talking about Cm naught wing, because Cm naught aircraft has Cm naught wing plus Cm naught tail plus Cm naught fuselage. So we try to calculate Cm naught wing, and this you know, if you check, is CMAC wing plus CL naught wing into XCG by C minus XAC wing by C. I hope you understand this expression. Remember, just to make things clear to you, if this is a cambered aerofoil at AC, the CL, CD, and there will be a CMAC wing, which has come because of transferring the forces. And typically for cambered aerofoil, this value is negative. And now suppose your CG is somewhere here. So at alpha equal to 0, there is a CL. So what will happen? This is CL naught. CL naught into this distance will give you a pitch-up moment. So here is typical case. So what is CMAC wing? I put the number which you already know, minus 0.116 plus 0.375 into 0.295 minus 0.250, which is nothing but this is XCG and this is XAC wing. If I do this, I can get CM naught wing. What question is coming to your mind? If you say this is given, 0.116 minus CMAC wing, this is XCG of the airplane, it is given. This is aircraft, right? It is given. XAC wing, 25%, 0.25 is also given. But where from I got this number? Suddenly I have written it, where from I got this number? So let us see, what is this number? This number is nothing but CL naught wing. How do I find CL naught wing? Let us see what is CL naught. We draw here. This is a cambered aerofoil. This is CL. This is alpha. So at alpha equal to 0, this value is CL naught. So how do I find CL naught? Simply this will be, since this is linear, this will be CL alpha into absolute value of this alpha, right? So CL naught will be CL alpha, which is 4.3 into epsilon alpha naught, and that is equal to 4.3 into 5 degree divided by 57.3. Why I am dividing by 57.3? Because this 4.3 CL alpha is per radian and 5 is in degree, alpha 0. So I have to convert degree into radian, so divided by this, and thus we get 0.375. Correct? This part is clear. So let me erase this. If I now erase this, I erase this also because now we are clear where from it has come. So this value will come out to be, I advise you to do yourself this so that even if some mistakes are committed, you should not get a wrong number. Okay, so this gets to minus 0.099 CM naught wing. Right? Well, are you happy? If CM naught wing is minus 0.099, then you know one thing for sure, that finally I want CM naught to be positive. That means major contribution to our CM naught should come from where? From horizontal tail by giving a tail setting angle. And that is perhaps 1 degree tail setting angle was given. Let us check that. Okay. We have seen we have got CM naught contribution from wing as minus 0.099. Now we want to find out what is CM naught tail for this configuration. But we know one thing, that if you want to trim the airplane as positive angle of attack, total CM naught should be positive. That means that whatever CM naught I get from tail, that should cancel this, nullify this, plus add some positive value. Okay? So let us see how much CM naught tail we get from this configuration. Going back to our expression, CM naught tail was given neta VH CL alpha tail epsilon naught IW minus IT. What was IW? Wing setting angle. IT, tail setting angle. And what was epsilon naught? Epsilon naught was downwash at alpha equal to 0. And when epsilon naught will be there? When there is a cambered aerofoil. Because at alpha equal to 0, there will be still lift for a cambered aerofoil wing. Lift means there is a pressure difference between bottom and the top surface, and there will be vortices which will give downwash value. And the expression to calculate epsilon naught is 2 CL by pi aspect ratio, and for alpha naught it is CL naught. So I am putting 2 into 0.375 divided by pi into aspect ratio of the wing. This is very important. We need to calculate epsilon naught using this. The values are known. CL naught is 0.375. Already I have computed that. aspect ratio we have computed to be 6.06. So if I use this expression, I get epsilon naught as 2.3 degree. Okay? So if I put all those things here, I could check neta again, I have assumed 1, VH 0.66, CL alpha tail 3.9, epsilon naught 2.3 calculated from here. 1 degree is the wing setting angle given. IT is minus 1 degree, so minus IT means minus 1 degree. But remember, this whatever degree is there, that has to be converted into radian by divided by 57.3, because this whole term is getting multiplied by 3.9, which is per radian, right? So if I do that, then I get Cm naught tail as 0.194. This is a wonderful number. You could see if Cm naught tail is 0.194, so Cm naught wing plus Cm naught tail becomes minus 0.099 plus 0.194. So you could see this is greater than 0, right? So how, by giving a tail setting angle of 1 degree, we have not only neutralized the Cm naught contribution because of wing, which is negative, we have also added some Cm naught value so that I can trim the airplane at positive angle of attack. That is, in pictorially, if I see, if this was the Cm naught wing, once I put the tail, what we have done, the tail setting angle, this Cm naught has now become positive. Okay, and something alpha can be trimmed at positive angle of attack. Okay, this is clear? So this is because of wing, and then somewhere because of tail is here. When I add this 1 and 2, somewhere I get here, which is this value. So indeed, it's a design where appropriate tail setting has been given, which is 1 degree, and also wing setting angle given, so that you find finally your Cm naught is positive. Okay, this is very important. So we have seen the contribution of wing, contribution of tail on Cm naught. We now know how to use these expressions, right? We now see how to compute the contribution towards stability. Now we are talking about contribution of wing towards Cm alpha or static stability. One thing a priori you know that AC of the wing for this configuration is ahead of CG of the airplane, so Cm alpha sign will be positive. So let us see what happens. If I write Cm alpha wing, which I have derived, which is equal to CL alpha wing into x CG by C minus x AC wing by C. If I now put the numbers, then it comes to be 4.3 into 0.295 minus 0.25, and this is 0.1935 per radian. So indeed, this is positive. It should be positive because AC of the wing is ahead of CG. Okay. Now see for tail, let's see what is the effect of tail. So you write again expression for Cm alpha tail, and that is given by minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. Neta, I take 1, VH I know, CL alpha tail I know. I don't know what is d epsilon by d alpha. So I calculate d epsilon by d alpha as 2. So I calculate d epsilon by d alpha using this expression pi aspect ratio wing. And if I put this number, I will get this as 2 into 4.3 by pi 6.06, and this is 0.45. Let me tell you, 0.45 d epsilon by d alpha is pretty high. You could see that. What is this expression? This Cm alpha tail. What is its role? It's a minus here. So this is basically stabilizing effect. If this number is more, if this number becomes equal to 1, then this will become 0. So we will try to design an airplane such that this value is as low as possible for stability, from stability point of view, right? So once I put that, I get Cm alpha tail as minus 1.42 per radian. Now I could see Cm alpha wing was plus 0.1935 per radian. Cm alpha tail is 1.42 minus 1.42 per radian. So this positive, which was destabilizing, this is negative, stabilizing. So when they have a combined effect, the aircraft, because of wing and tail, has Cm alpha negative. That means it is statically stable, right? Okay. That is, in a way, we have now seen what is the role of horizontal tail. You could see a destabilizing configuration has been converted into stabilizing airplane by using appropriate tail. And also, tail has a contribution to a stream. By giving setting angle in the tail, the Cm naught has been made suitably positive. Okay? This is the beauty of this term. As a designer, you need to use it more frequently. Okay?